We've now seen how we can write functions in OCaml that work with structured data. As we dive deeper now into the power of functional programming, let's start with some examples. Let's say we wanted a function that would increment all of the values in a list by 1. For example, if the input list was 314, then we would want the function to return the list 425, the same list, but with each element increased by 1. We could define this function recursively. It accepts a list of integers, we'll call this list x's, and it returns another int list. How do we work with the list? As usual, we'll start by pattern matching it. If the list is empty, then the problem is easy. The output list will also be empty, since there are no values to be incremented. Otherwise, if the list has a head and a tail, we have a little more work to do. What does it mean to increment all of the values in the list? Well, the head, the first element in the list, will need to be incremented, and that will be the first element of our new list. But what comes next? Well, all of the elements in the tail will need to be incremented as well. To do that, we can recursively call our function, which will increment all of the values in the tail of the list. This function works because each time the function is called, we increment the head of the list, and then recursively call the function on a smaller list of remaining values. Take a look at this function a few times and make sure you really understand how it works before moving on. Now let's try another example. Let's write a function to square all of the values in a list. If the input list was 314, then the function should return the list 9116, the same list but with each element multiplied by itself. We could again define the function recursively. It takes a list of integers as input and returns an int list. We match the list. If it's empty, then the returned list should be empty too. If there's a head and a tail, then we multiply the head by itself and cons it with the output of recursively calling the function on the tail of the list to square all of the values in the tail. So here are our two functions, one that increments all the values in a list, and one that squares all the values in a list. They do two different things, but you should notice that these two functions are remarkably similar to one another. Much of the code is actually the same, and we've just written it twice. This leads us to perhaps the most important edict of programming, the edict of irredundancy. Never write the same code twice. There's a high cost to having the same code appear twice or more in a program. If there's a bug in one copy, it needs to be fixed in all the copies. If we make a change to one copy, that change needs to be made to all of the other copies, and so forth. It would be much better designed to take the code that is the same, the underlying identity, and factor it out, using an appropriate abstraction mechanism like a function. So what do we do in the case of these two functions? They're not entirely identical, but we have definitely written the same code twice. We just need to identify what's different and what's the same. What is the underlying identity between these two functions? Once we do that, we can factor it out and make our code much cleaner. In this case, the structure of these two functions is the same except for this section on their last lines, where we perform some computation on the head of the list. In one case, we're adding 1. In the other case, we're multiplying the number by itself. How would we characterize what's happening to the head in each case? We could describe what's happening to the head of the list using a function. In one case, we're essentially applying a function that adds 1 to the head of the list. In the other case, we're essentially applying a function that takes its input and multiplies it by itself. These two functions are the essential difference. But other than that, these two pieces of code are doing the same thing. They take a list and generate a new list, which is the result of applying a function to each element from the original list. So let's define a function to capture this abstraction that will then help us remove the duplication in our code. Conventionally, this process of performing an operation on all elements of a list is called a map, so we'll call our function map. The first argument to map will be a function f. F is a function that will take an integer as input and return a new integer, but as long as it follows those constraints, it could be any function. Maybe it adds 1, maybe it squares the number, maybe it does something else. We're defining our map function to be general so that it works no matter what the function does. The next argument will be the list of integers we want to apply the function to, and the output will again be a list of integers. As before, we start by matching the list. If it's empty, we return the empty list. If the list has a head and a tail, here's the interesting part. Before, we applied a particular operation to the head of a list. This time, in our more general map abstraction, we're going to apply the function f to the head of the list. Then, we're going to cons it with the result of recursively calling the map function. The map function takes two arguments. First, the function f that we want to map over the list, and then the list of elements to map over, which in this case is the tail of the list. So let's recap what this function does. It takes a function f that operates on integers, and then a list of integers, and outputs a new list that's the result of applying the function f to each element in the list. As a result, the type of this map function is int to int list to int list. The first argument is a function from integers to integers, like a function that adds 1 or any other function that takes an integer as input and produces an integer output. The next argument is the list of integers to map over, and the output is a new list of integers. This is a higher order function, where we're dealing with functions that take other functions as input or return functions as output. Now that we've defined our map abstraction, let's use it. We can map a function that adds 1 to an integer over the list 3, 1, 4, and we'll see that the output is a new list with each element incremented by 1. We can use the same map function to map a function that squares an integer over the list 3, 1, 4, and we'll see that the output is a new list with each element squared. Let's go back to our original definitions for these two functions. Using our new map abstraction, we can simplify these definitions considerably. To increase all the elements of a list by 1, we just map a function that adds 1 over the list of elements. To square all the elements of a list, we just map a function that squares a number over the list of elements. We've made our code much simpler by identifying the underlying identity between these two functions, mapping over a list of elements, and factoring it out into its own abstraction. There are other improvements we can make here too. Remember that functions in OCaml always take their arguments one at a time. When we have a function that appears to take multiple arguments, it's actually just a curried function that takes a single argument and returns a new function that takes the remaining arguments. That insight enables us to use a technique known as partial application, where we apply a curried function to only some of its arguments, resulting in a function that takes the remaining arguments. Take, for example, this function that takes two integers and adds them together to get their sum. If we apply the function to two arguments, then we get the sum of those two values. But if we apply the function to just one argument, then we get a function that's waiting to take the second argument, and then we'll compute the sum. We can even give a name to this partially applied function. We might call a new function increment, for example, and define it to be the result of applying the add function to the number 1. Increment is now the result of partially applying the add function. It's a function on its own, and when it's applied to an argument, it will add 1 to the argument. Partial application lets us take curried functions and define other functions by applying the curried function to only some of its arguments. Map is one such example of a curried function. Recall that its type is int to int list to int list. It takes two arguments, the function we're going to map over the list, and then the list of elements to map over. But the arguments don't need to be provided all at once. They can be provided one at a time. So we could just apply map to the function that increments a value by 1. The result is a function of type int list to int list. It's a function that will take a list of integers as input and return a new list of integers with each value incremented by 1. So this by itself is a valid definition for our function to increment all of the values of an integer list by 1. And we could use a similar definition for a function to square all the values of an integer list as well. Using the map abstraction and partial application, we've greatly simplified these two functions from what they looked like originally. The map abstraction is useful anytime we want to take a list and produce a new list with some function applied to each element of the original. But there are other abstraction opportunities we can find by looking at other similarities in code. Let's look at a few more examples. Say we wanted to define a function to compute the sum of a list. For the list 1, 2, 3, 4, 5, the function should return 15, since that's the result of adding 1, 2, 3, 4, and 5 together. Here's how we might do that. The function will take a list of integers and produce an integer as output. We start, as we often do, by matching the list. If the list is empty, then there are no elements to sum up. The sum is just 0. If the list has a head and a tail, how do we get the sum? Well, we can recursively call our function to sum up the tail and add the head to that. Whatever the sum of the tail plus the head is, will be the sum of the entire list. Let's try another example. Say we wanted to define a function to compute the product of a list. For the list 1, 2, 3, 4, 5, the function should return 120, since that's the result of multiplying 1, 2, 3, 4, and 5 together. Here's how we might do that. The function will take a list of integers and produce an integer as output. We match the list. If the list is empty, there's no more elements to multiply, so we need to return some initial value. Since multiplying by 1 doesn't change the value, 1 makes sense as the initial value here. If there's a head and a tail, then we need to get the product of all of these elements. We can do that by recursively calling our function to take the product of all the elements in the tail and multiply the head by the result. These two functions are correct, but let's again look for the underlying identity. Where are they the same, and where are they different? This time, the two functions differ in two key places. They differ in the initial value that we use for the empty list. In one case, the initial value is 0. In the other case, the initial value is 1. They also differ in what operation we use to combine the head with the result of applying the original function to the tail. In one case, we add. In the other case, we multiply. This kind of pattern, where we start with an initial value and then combine all of the elements of a list by processing each element one at a time, is called a fold. So to simplify our code and avoid redundancy, let's define a new function for folding. Here's how the fold abstraction is going to work. We're going to keep track of some value, often called the accumulator. That accumulator has an initial value. We're going to go through the list one element at a time. For each element, we're going to apply a function that takes the element and the current value of the accumulator and gives us a new value for the accumulator. We're going to do that with each element in the list until we get a final value for the accumulator, which will be our answer. Why do it like this? Well, let's see how we can take this general pattern and use it to compute the sum of a list. The accumulator is going to keep track of the sum so far in the list. Initially, it's set to 0. When we process our first value, we'll apply a function to the element and to the accumulator, which is currently 0. In the case of summing a list, this function will just be a function that adds two numbers together. So in this case, adding 0 to the element leaves us with just the same value of the element. That becomes the new value for the accumulator. We then move to the next element in the list and apply the function to that element and the new accumulator, getting a new running sum. We keep repeating that process for each element in the list until eventually we process all of the elements. The final value of the accumulator is the sum of all the elements in the list. The same pattern works for computing the product of all the values in a list. The accumulator will keep track of the running product. Initially, it's set to 1. This time, the function we're going to use is a function that multiplies two numbers together. So when we process the first element, we multiply by the accumulator 1, and we get a new value for the accumulator. We keep taking elements of the list one at a time and multiplying them by the accumulator to get a new value for the accumulator. And once we process all of the elements, we've got a final value for the accumulator, which is the product of all the elements in the list. Now that we've built up a conceptual understanding for how fold is going to work, let's write the code for it. The first argument to fold will be the function we're going to apply to each element. Remember that this function needs to take an element of the list and the current accumulator and return a new accumulator. So its type is going to be int to int to int. It takes two integers, the element and the accumulator, and returns a new integer accumulator. Next, we'll need the list of elements to process, which is an int list. But finally, remember that we'll also need an initial value for the accumulator, which will just be an int. The return type of this whole call to fold will be the final value of the accumulator, which will also be an int. So what goes in the body of the function? We'll start by matching our list of values. If the list is empty, then we're starting by returning whatever the initial value for the accumulator should be. But what if the list has a head and a tail? Well, now we need to apply our function f. Remember that the function needs to be applied both to the current element of the list and the current accumulator, which is the result of folding over all of the elements that come after it. So we'll apply f to the head of the list, and then we need to apply it to the result of folding over all of the elements that come after it. To do that, we'll recursively call the fold function. The fold function, recall, takes 3 arguments. First is the function, that's just f. Next is the list to fold over, that's the tail of this list, the remaining elements that need to be processed. And finally, we need the initial value for the accumulator, which is just init. This then is our fold abstraction. Its type is int to int to int, to int list to int, which is one of the more complex types we've seen in OCaml. But it makes sense if we look at each part of that type and understand what each part is doing. First, we need a function that takes 2 integers and outputs a third, maybe a function that adds 2 numbers or multiplies 2 numbers. Then we need an integer list to process. Then we need the starting value for the accumulator, and then the output is some integer result. Looking at that type helps us figure out how to use the function. We can define the sum function using fold. First, we need to provide fold with a function, so we'll use a function that adds 2 numbers together. We could write the whole function out ourselves, but remember that the addition operator can be treated as a function if we wrap it in parentheses, so that lets us be a little more concise. Then we need the list to process, and finally we need the initial value for the accumulator, which is 0. This definition of sum is much more concise than the version we had earlier, and we can define a function for getting the product of all the elements in a list in a similar way. Instead, we'll just use the function for multiplying 2 numbers together, and we'll let 1 be the initial value for the accumulator. There are a lot of problems that can be solved using the fold abstraction. Imagine we wanted to write a function to compute the length of a list. How could we do that? Well, let's try to use fold, where we have the accumulator keep track of the length of the list so far. We can start by calling fold. What function should we provide to it? Well, if we have a head of a list, and we have the current value of the accumulator, which is the length of the tail, then the new length is just 1 plus whatever the current accumulator is, since we're processing 1 additional element. We're folding over the whole list of elements, and the initial value for the accumulator is 0, since an empty list has length 0. Just like that, we've used the fold abstraction to very succinctly define a function that takes the length of a list. Since our fold abstraction processes elements from right to left, it's often called a fold right. We could also define a fold left that processes elements from left to right instead. But let's look at one final abstraction, again by noticing patterns of repetition in other code. Here's a function that takes a list of integers and returns a list of only the even numbers from the original list. It works by matching the list. An empty list has no numbers in it at all, so we return an empty list. For a list with a head and a tail, we first check to see whether the head is even or not. If it's even, then we cons the head onto all of the even numbers in the tail. Otherwise, we ignore the head and proceed to compute the even numbers in the tail. And here's a function that takes a list of integers and returns only the positive ones. It again matches the list. For an empty list, we return the empty list. For a list with a head and a tail, we first check to see if the head is positive. If so, we cons the head onto all of the positive numbers in the tail. Otherwise, we ignore the head and return just the positive numbers in the tail. Again, notice the similarities here, and see if you can try writing a function that factors out the underlying identity. These functions do essentially the same thing. They're taking a list and returning a new list of only those elements from the original list that have a particular property, like being even or being positive. We call that abstraction a filter. We can define a filter function. Its first argument will be an int to bool function that takes an integer and returns true if it should be included in the output list, and returns false if it shouldn't be included in the output list. Then, its second argument is the list to process. The function returns a new list with only the elements that satisfy the predicate function in the first argument. To implement the filter function, we can start by matching the list. An empty list returns an empty list. For a list with a head and a tail, we apply our predicate function to the head. If it returns true, we should include the head in the output list, so we cons it on to the result of filtering through the tail. If it returns false, we shouldn't include the head in the output list, so we just return the result of filtering through the tail. This allows for simplified definitions for our functions to filter even numbers or filter positive numbers by avoiding redundancy. We arrived at the map, fold, and filter abstractions all by looking at code and determining the best place to carve our software into different pieces. This is the edict of decomposition, to carve software at its joints, the natural places to cleanly break our code into pieces. By separating map, fold, and filter into their own abstractions, we were able to greatly simplify pieces of our code that previously shared a lot of underlying commonality. These kinds of abstractions are so useful with lists that OCaml makes them available to us in the built-in list module. We'll talk more about modules later in the course, but for now, know that you can use the functions list.map, list.filter, list.foldRight, and list.foldLeft to use these abstractions without needing to write all of the redundant code yourself.